Good evening, all. Welcome to Coding Club's interactive session, day 5. Today, we'll be discussing convolutional neural networks. Okay. We have a slight issue. One sec. All right, we'll be waiting for another 5 minutes before we officially begin. Okay, so now we'll officially begin. And if you've logged into your Jupyter Hub account, you'll see that there's already a new folder here, 04 CNN. So when you open that, you have a Jupyter notebook there, cnn.ipynb. And in there, you see there's this image. This describes various stages of what a very simple convolutional neural network would look like. But before we go into this detail, and there's a link here as well, and we'll get to that later. But before we get into these details, first I would like to pose a question. How do computers see? Or rather, if we are analyzing a particular image on a PC, what exactly does the machine see in a particular image? So for that, uh, there are several stages to this, and so the first thing that we need to answer again is what are images anyway? So images are just numbers, as many of you would already know. They have You can have RGB images or grayscale images, and they can be simply pixel values from 0 to 255. And if it's RGB, it'll have three channels. If it's grayscale, then it'll have a single channel. And uh, okay, so before we get to that, let's first answer, how do humans understand or interpret an image when they see it? So we look for different uh, uh, objects inside the image. We look for, let's say, edges, or let's say if you're looking at a face, we'll be looking for things like the edges of the face, the curves, and all that. And then that will be the lowest level of the lowest level interpretation of what we're looking at. Then when we go to the medium level, we'll have things like the organs, the eyes, the shape of the eyes, the color of the eyes, the nose, the chin, and so on. And then at the very highest level, we detect that it's a face or the facial structure overall. So, how do we do that? How do humans do that? Well, we have something what we would call domain knowledge. So, uh, this term will come again and again in today's session. And so, let me actually go to this journal, and let's say I draw a simple image. Let's see. In the invitation mail, we had actually promised cats. So today's whole exercise will feature cats heavily. Okay, so let's say I have an image, very simple image, obviously, of a cat. Pardon my drawing. I'm not too used to this. All right. So let's say this is an image of a cat. Then if we put it in a PC and if we plot it, then we'll simply have a grid representation of the same image. They'll have several rows and several columns, and each of those will have several pixels. Or if you go down to the pixel representation, the individual pixels, then you'll have uh, a particular number associated with each of these pixels. So this will be seen by the machine as, okay. Let me edit this a bit. All right. So yeah. So this will be seen by a machine as, okay, something wrong with this here. Okay, no, fine. So, so you'll have several columns and rows, and in each of these uh, grids, you'll have a particular number from 0 to 255. Let's say this is a grayscale image. In that case, you'll have only one layer. If, say, this was RGB, uh, then in that case, you'll have stacks of these. So you'll have like 3 different stacks corresponding to each channel, red, green, and blue. So this would be for R, then this would be for green, and this would be for blue. Okay. So for simplicity, let's just stick to grayscale. The data that you'll see. So if I go back to the Jupyter Lab interface, you'll see that there's a file there called data.npy. So that's the data that we'll be using today, and it's a collection of grayscale images. We'll get to that, but for now, let's see. Let's come back to the question that I posed earlier. What do computers see in this grid of numbers? So let's say if we want to detect that this is a cat, for humans it's very easy because we already kind of know what a cat would look like. So it'll have a tail, it'll have 4 sets of legs, then the ears and the facial structures. We kind of have some sort of idea of what a cat would look like. That's what we refer to as domain knowledge. But to a computer, again, this is just a collection of numbers. So how do we go from this collection of numbers to domain knowledge that a computer can understand? Just give me a sec. I'm not at all used to this. Okay, so now our task is to filter out some important aspects of the image, obviously in the form of numbers. That's what a computer understands, and then tweak it in a certain way so that we have some things called features. Now, features form an important part of domain knowledge. So, features. Uh, okay. Hmm. Okay. So now, how do you define features? So, if it's a image of a cat, as I mentioned earlier, you look at the whole structure. Let's say the structure of the body. So, so let's say if you're looking at the face in particular, then you have the ears, the whiskers, and so on. Uh, so, how do we translate this? So, in yesterday's session, Spandan mentioned a particular kind of network called feed-forward network, or FFN, which was simply okay, multiple linear layers connected together, densely connected together, in fact. Uh, but there we saw that we had connections of the form. Uh, you have a particular neuron in one layer, let's call it L1, and in the next layer, you have a set of neurons, or let's put any random layer in the middle, and you have all of these neurons in one layer. All of these are connected to layer 2, and then uh, so on in the entire architecture of the model. But what happens if you apply this to the task of computer vision or image classification? uh, in that case, you lose all the spatial information that you have. And the reason for that is quite simple. Let's say this is n dimensional. Let's say you have n neurons in this layer, and you have, let's just, for the sake of simplicity, consider we have only one neuron here. Then what you're trying to do is you're converting n dimensional data to one dimensional data. And in doing so, you lose all the spatial information that any particular image had. And that is quite important, obviously, because as I mentioned before, what we look for and what we want a machine to look for are features. And these features, let's say for a face, the ears, whiskers, the position of the eyes, they matter. The spatial uh, structure of the image would matter. So uh, in that case, we can't use FFN. So now there are multiple approaches to this, and the main topic of today, that is CNN, is one of the better approaches that we have been, or humans have been able to come up with. So we'll get to that. So what is CNN? Let me just create another. Leave it. All right. So what is a CNN? So you have convolutions, or rather the C in CNN stands for convolutional, and then N and N, obviously you know that they stand for neural networks. We have been doing it for the past two sessions. All right. So we know what this means. Let's try to understand what convolutional means. So at the root of this term, convolutional, or this architecture model in general, is a special operation called convolutions. Okay. So what are these convolutions? Uh, so I mentioned in the image that I drew earlier that when we have an image which is just a grid of numbers, and we want to obtain information on like specific features of that image, depending on our problem at hand. So let's just consider the problem of image classification. So we want to label what the subject of the image is. So if it's a cat, then we'll label it. We'll first try to understand what the features are, and then we'll label it as a cat or not cat. So in a particular image, and we also saw that if we apply FFN to it, then we lose the spatial information, which is quite necessary. So uh, okay, so let's say we have an image again, and let me just draw a simple stick diagram this time. Let's say this is a cat. This, and I'll leave out. All right. And we want to detect whether or not this image contains a cat or not. So we see that the pixel representations will have different kinds of different parts of this picture in different regions. So the idea behind convolutions and CNNs is that we, instead of looking at the full image as a whole, what we do is we apply a sort of patchy operation to it. So what we do is we put a we create a filter, a really small filter, as compared to the whole image size. We can and we slide it across this whole image. So this filter is also called a kernel, or even just a window in some cases. So we'll be sticking with the word filter for this session. So okay. So what does this filter do? So we know that this image is just consists of numbers. So we have numbers from 0 to 255 here, assuming grayscale image here. And in this filter, we have to choose a set of numbers. So let's say in this particular case, I just go with 1111, and here 0 to 255. So okay, let me make it finer in this case. That will be easier. Assume this is a very simple image. So we all we have is, instead of even 0 to 255, we have something like okay, let me edit this. This is like a binary image. So what you have, instead of 0 to 255, you have 0 to 1. So the values are from 0 to 1. And our filter, or this kernel here, has all ones. And then we slide it across. So what happens if we apply it here? This is all zeros. As I said, it's a binary image. So you have only zeros or ones here. And you'll have ones where the picture actually is. So like if this is finally, if I go for a finer grid here, then you'll have this will have something like 1 here, nothing over here, then perhaps a 0 here, and let's say if I extend the leg here, then something like 1 here. A very simple image. But in this case, we have all zeros here. And what we do, what a convolution is, you have this filter. What you do is, since this is a grid of numbers, this is again a grid of numbers, we can represent them as matrices, and just take an element-wise product, not a matrix product, in this case, an element-wise product. So we have a filter here. We have the whole image here. We put it at, let's say, one end of the image, and we just multiply element wise. So if we multiply the values here with this particular portion of the image, then we'll obviously get all zeros. So the output here for that particular corner only would be all zeros, and then so on. So we slide it again. Let's say we go to an area where it's something like, okay, let me just represent matrices now. That will be easier. So this is a area where, let's say, the values are somewhat like 1, 1, 0, 0. And then we take a product, element-wise product, with our filter here. Then what do we get? We simply have a 1 and 1, and this becomes 0 and 0. So you kind of see what we are going for here, right? So this, in this image, this particular area of the image that we took, this can be taken to be uh, a particular, this can be taken to have a particular feature that we are interested in. And this is our filter. So this filter, what does it look for? This is clearly looking for spots in the image, spots of like 2 by 2 spots. So you have, in the image, you'll have something like, okay, sorry, let me just edit this out. Okay. So let's say if you have in the larger image, okay, so in the larger image, let's say what we are looking for is in the central area. So like if it's a binary image here, then this particular portion, let me change the color, although this has become very dirty here, but let's just say in the central area, if you take a portion of that out, then we'll have something like this. So you see that, okay, let me move here. You see that in the central area, we just have a straight line kind of. So if we represent it in matrix format, then we'll have something like 0, 1, 0, 0, 1, 0, and then so on. These will be all zeros, these will be all ones, and these will be all zeros again. So, and what we are interested in, or let's say if we add a bit of thickness to it, then we can have, let's say, 2 rows of all ones. So we can have something like this, we can have another row of ones here, and so on. So let's say if, so yeah, so coming to our filter now, let me go back to white. Okay, coming to our filter now, we see that the way this filter is designed, it's all ones. So what it will be looking for is in fact these sections. Sorry, my bad. Let me just undo that. Okay, so what we're looking for are in fact these sections. So if we run our filter on, let's say, the this whole section, then what will result in is again just uh, a series of just 2 rows full of ones. If we run it on, say, the first 2 rows here, zeros and then ones, then we'll have something like uh, again 0, 1, and then so on. So in essence, what these filters would do is collect local information and then output. So the overall output, which we actually call feature maps, although we are missing a particular step, but we'll get to that. So let's just call it like the first stage here for the creation of a feature map. So so what these filters do after this multiplication process is output a matrix again, and this is like stage one of a feature map. And so you can see that these preserve local information, and this is operation that we just did, this whole element wise multiplication with a filter which we create, uh, is what a convolution is. It's as simple as that. So we have the image, we convolve it, okay, convolve, which is a verb. We have an image, we convolve it with a filter that we create, and what it outputs is a feature map. What the feature map contains is distilled information, uh, distilled information of the image in terms of only the things that we're interested in. So the things that we're interested in are what we labeled as features. Okay, so then we have this. Also, another thing is that we don't have to stick with a single kind of filter. We can have as many kind of filters as we want. We can, let's say, if I wanted to look for in this particular image, let me clear it out a bit though. Or better to just read the whole thing. Okay, so let me have a okay. So in this particular image, if I was looking for um, let's say the okay, so yeah, in this particular image, if I was looking for, let's say, the ears, what kind of filters would I go for? We see that for ear, it's kind of slanted and so on. So what we would do, let's say this is an image patch of that particular area, then our filters should kind of look like uh, yeah, these are angle, right? So we'll have something like diagonal ones, let's say, and we'll have zeros here and so on, and then we slide it across the entire region or the entire image, and then that will result in a feature map, which should give us something like which, if we plot as an image, will give us something like a diagonal line. And so we can have different kind of filters, and we can stack them together. So if I go back to my uh, yeah, the Jupyter Lab session, you can see that in this image, you have an image of a car here, which is the input. Then what you do is you apply a convolution on it. And this convolution is taking a particular image or a particular patch or a region of the image, and then applying convolution on it. And then this results in a slightly smaller uh, map of the image, which stores all the information, of course. It has the domain knowledge, it has the knowledge of the features, and that's why it's called a feature map. And then what we can do is we can uh, stack these different convolutions with different filters, and as we do that, we distill more and more information. At the same time, we still preserve the local information. So you have convolutions with ReLU and so on. So yeah, coming to this ReLU here. So yesterday, I think Spandan mentioned that ReLU is simply rectify linear unit. It's a kind of activation function like sigmoid. This is in fact simpler. It's given by just max of 0 and x. So what it will do is okay, let me just draw ReLU. So what I'll do is, let me say this. Totally not used to this. Okay. Uh, so what ReLU would look like? It's just max. Let me define it. Z of x would be base. All right. So Z of x simply max of 0 and x. And the plot is quite simple. It'll just look like this. This is G. This is x. G of x. So you see that anything below 0 is suppressed. So it's just brought down to 0. But anything above 0, if your input value is above 0, then it will just output the same thing. So what you're doing essentially is uh, promoting, first of all, absolute or positive values. And secondly, you're promoting non-linearity in your feature maps. So after, let's get back to the convolution operation. So you have an image, you convolve it with some filter, a smaller filter, obviously. Then you get a feature map. And here in the feature map, to each element, what you do is apply this activation. So you'll have something like, okay, so you'll have something like, let's say if you have negative values here, some negative values, whatever they may be, and then some positive values, what you do is you want to suppress the negatives. So you put it through the activation function. What you'll get is, for all the negatives, you'll get zeros. For all the positives, you'll simply get what they were. So there are various reasons to do this. One is stability, and the later half when we are actually calculating the overall error. But another reason is that this function here is clearly a nonlinear function, and the real world data, more often than not, is nonlinear. It's very rare to find something that is linear and nice and well behaved. Most of the cases, even in very simple images, even if you distill out a lot of clutter, you'll still find that the input image is input data is nonlinear. So this has a twofold purpose. One is obviously for stability in terms of error calculation later on while we are training, and the second is to introduce non-linearity to your network. All right. So okay, so that's what ReLU's purpose is. It's an activation function. Now let's go back to this, and then we see that there's another step here that is pooling or downsampling. So let's get to that. Uh, Although from the image, I think it's clear that what's happening here is with each of these convolution operations, what you're doing is you're downsampling. So you have this large image, you put it through a convolutional layer, then you get a small image. Then if you pool, then you again get a small image. So what you're doing is you're downsampling all the information. So this is what I meant when I said earlier that if you distill down the information, you'll still be preserving. So okay, let's say take a random matrix, or okay, let's just go back to this here. We have a matrix here, 0 0 and 1 2. Let's use that. It is 0 0 and 1 2, right? Yeah. Okay, let's go with this. This is our 2 by 2 filter, the output from the 2 by 2 convolution operation. And now what we want to do is we have put it through our activation. Now let's just put it through a pooling operation. So what does pool mean in this case? So what we're trying to do is uh, so the whole pipeline of this CNN is you have a image, an input image, a large image. You convolve it with some filters, a set of filters. You get a representation, a smaller representation of the full thing. But then even among these features, I mean, even in this subset of a feature map, what features do you select? That's where this pooling operation, sorry, my bad. Me back. Okay, that's where this pooling operation would come in. Uh, so what you do is you have these four values here, and let's start with a very simple form of pooling called max pool. So what you do is for all of these values, you just consider or take the maximum value. So here in this case, it's 2. So what you'll output is just 2. So it's from 2 by 2, it just becomes 1 by 1, and so on. And you do this for each of the windows. So if you have multiple outputs, let's say if you have, let me get rid of this. Sorry, I should just, okay. Right, so let's say if you have multiple outputs from after applying your convolution. So for any image, what you'll have is another set of values. So smaller in size, overall shape rather, matrix shape, but you'll have another set of values. So now let's let it in terms of the filter values. So let's say after applying everything and the convolution operation and ReLU, you get something like some zeros and then some positive values and so on, whatever they may, and so on and so forth. So then what you do is you apply a pooling operation on it. So what pool would do is, let's say if you are pooling, if the size of, so okay, as I showed here, let's say if you're pulling per filter, then and if you're max pulling, so what we'll do is in a particular kernel or a filter, we'll just take the output from a particular kernel or filter, we'll just take the maximum out. So after applying a pooling, what we'll end up with is simply the maximum of that. So okay, this side isn't working fine, but all right. So okay, so the maximum. And let's say if you had something else here, like zeros, x, 5, and 9, or whatever it may be, we'll just take the maximum out, and that's it. Now, this is one way to pool. There are other ways also to do the same operation. For example, if you want to put weights on particular features, like while extracting particular features, there's another method that we can use. That's called average pooling. What it'll do is it'll calculate average of all of these values, then put it in here, and then it'll do it for all of these filters, all of these filter outputs, and so on. But for today, I'll just stick with max pooling. It's simple and it works in for a lot of image classification tasks. So, okay, returning to our Jupyter notebook. So we know what convolution is now. We know what ReLU is. It's an activation function. The pooling operation. Yeah, so this is also quite naturally called the downsampling operation. So what it will do is what it is doing is it's sampling information or filtering out information from the image at several steps, and uh, and at each step what it's doing, it's downsampling the information. It's filtering out the unnecessary parts, or the unnecessary parts defined by us through our filters, through our convolution filters, and then it's filtering those out. So what we're left with is a much cleaner representation of what the input data was. So in the end, you can see in this image as well, you'll have something like this, a final feature map, which represents this image, but in terms of the filters that we want to, that are important to us or to the problem, to the task at hand. And so this is just what CNN, this is the core of what a CNN would does. And this is also called feature learning or feature extraction. We'll come to what this means and the importance of it a bit later. Okay, so now we are ready for classification because we have already distilled down the important parts of our image into a final feature map. And now we're ready to classify, look at the image and then classify or predict probabilities in particular. Okay, let me save this again. Create a new one. Okay, so all right, so we had our image. We put it through the convolution operation, conv plus the activation, and then pool as well. Let's say that gave us a feature map. Now, okay, another thing is these don't have to be 2D matrices. So I'm drawing it as 2D matrices, but as I said, for example, even for the input, if it's RGB, it will be 3 different stacks. So it will be, let's say, if the width and height are W and D, you'll have 3 different channels because of RGB. That will be, sorry, it will be P cross W cross D for an RGB image. Only for a grayscale image, you can find something like 1 cross W cross D, but then you can just drop this one and call it a 2D matrix. But this operation, what I defined it, in my examples, I used only 2D filters, but you can have it for 3 dimensions, of course, and then 1D again. For 1D data, like for example, a time series, you can have one-dimensional data, and then you can have one-dimensional filters. Okay, so okay, so let's say this is a 2D image, so we'll just call all of these as con 2D, and then pooling operation is also in 2D. So in the end, we end up with a feature map. Now this again does not have to be 2D, even for two-dimensional data. So it again depends on the kind of parameters you choose for all of these operations, the convolution operation, the pooling operation. But again, for the sake of simplicity, let's say that it is 2D. Then after this, after we have this feature map, this is our feature map. What we can do is we're ready to classify basically. So let's say if our initial task was, okay, let me write it in the corner. The initial task was to classify whether or not an image has a cat or not cat. So our task is simply cat or no cat. Okay, so this is a binary classification problem. So in the session yesterday with the MNIST data, we had different digits, like 10 digits. And there what we did is we had multiple layers to the, okay, let me digress for a bit here. Okay, there we had, let me avoid that corner actually. So, all right. So, okay. So in the FFN yesterday, we had multiple layers, completely connected or dense, and in the final layer we had another fully connected layer, which was something like this. So you had 10 of these neurons here, corresponding to your 10 classes or 10 digits in the final layer. So this is the final layer. Let me get rid of 2 here. Let's just call it final layer. All right, and this is some layer L2, whatever ln. You'll have multiple layers here. In the final layer, you'll have exactly 10 of these neurons with their own activation functions and all. Because you had, and the reason for that was because you had 10 digits. Today, we are considering this task, whether the image contains a cat or not a cat. So this is a binary problem. So here, you might have guessed it already, but we need only 2 neurons in the final layer. So in our so after we have the feature map, what we'll do is this will be we're assuming it to be a 2D feature map. Then what we'll do is we'll flatten it. So the flatten operation is simple. Simply okay. Let me get rid of this line here. Okay. So the flatten operation is simply taking the elements and then arranging it in a particular fashion. So usually what we do is for each we have multiple rows here. These are stacked vertically. What you do is for each of these rows you stack them horizontally like this, which the final output obviously is a one-dimensional array, and that's why we just call it flatten. There are multiple ways to do this, but for simplicity, again, let's just consider this. So if it's say w by d, if that is the dimension of this matrix here, then finally you'll have just a 1D array of shape, or not of shape, but of length w into d. It'll be simply be a 1D array, and this can be represented again like we did with the feed forward network as a set of neurons. So okay, let me move this to this side. Okay, all right, that's that. Okay. Like with the FFN, what we'll do is in the layer, let's say one layer before the final layer, let's just call it like n minus 1, and then you have ln, and then this is the final. Let's put it that way. In the final layer, we'll have 2 neurons because we have 2 classes. But in the layer before that, it will have w into d number of neurons. So what we did is we had leave this aside. Then we had a feature map, this particular array, w that way the width and the depth. Or okay, so in this case, let's instead of calling it depth, I suppose it's better if I use the term height since it's just 2 dimensions. So okay, let's move all this. So my bad, I'm calling it WD again. Okay, so one okay, so I think we all right. So let's just stick with WH here. The conventions vary across multiple packages. For example, we are using PyTorch, so there the convention is in fact to use I think width and height, but in TensorFlow it's the other way. There sometimes H and D are interchangeable, the height and the depth. All right, so we have so let's say we have a feature map, the height and the width, and in this layer it will be a dense layer, or in PyTorch lingo we saw yesterday the linear layer. That's the dense layer. So it implements a simple weighted pass of this form. It will simply take the feature map and then convert it into a set of neurons, which are the number of which is W into H. You'll have that many neurons here, and then all of these are connected again with the two neurons in the final layer, densely connected. So you'll have each of these being connected to these two neurons, and so on. Sorry. All right. So let me get rid of this. Okay. So that's what you see in the final classification layer. So you flatten them, then you have some fully connected layers. We can ignore softmax for now. We'll not be going into that today, although it's recommended, but we don't really need it. So what we'll do is we'll have a layer, one flatten operation, and you have a fully connected layer, and then that's where we'll end. We'll just have two neurons in the final layer, which will store the probabilities of the two classes, the cat and not cat class. So this is how this full convolution neural network works. A very simplistic overview of the whole thing. So now we'll get into the code, but before that, let's just take a 5-minute break. And if you have any questions, you can direct it towards me or the volunteers, and then we'll just head into the coding part. All right, so we are back. Uh, okay, so yeah, one before I move on to the code, one thing that I missed was a very special property of the convolution filters, which is in fact what makes them so special in the field of deep learning or neural networks. So let's say we have an image. Let me go to that here. We have sorry, not at all used to this. Okay. All right. So we have an image. We have the filter with. Let's just consider them together. So this time, this represents our convolution step plus the activation plus the pooling step. So let's consider them all together. Although what we're interested in right now is only the convolution operation. So in this filter, whatever filter we choose, whatever kind of filter we choose, depending on the features we want to detect. Uh, let's say if it detects, let's say if you have a filter of the shape, yeah, let's take an example of something like this, and these are all zeros, just the identity matrix. So obviously this can be used for detecting the slopes or the slanted lines in an image. And the special feature is that all of these filters are uh, translation invariant. And this is what makes convolutional neural networks special. So these are translation invariant. What we have been doing across all of this is we take a filter, uh, we place it on the input image. We take a filter, put it on the input image, and then we slide it across. Let's say we first go row-wise, and then once we are done there, we'll come back here, and then we'll slide again, and then so on. So if a particular filter, like for example, this detects these slanted lines in an image, then it doesn't matter what the input image would look like. So for example, if you have something like this, let's say if this is an input image of an X, and we use this filter, and so if we put it on the corner, it'll detect a line and then slide it across. Let's say when it comes here again, it'll detect something like this. And if we change our input image to something say, like this, like a curly X, even here you can make use of the same filter. So it doesn't really matter because you can see that even this X has these slanted lines in the middle. You can use the same filter here and slide across the image, and you'll get similar values like you would for just a very well shaped X. And this is the translation invariant property. So it doesn't matter. So the image in particular, it doesn't matter what your input image looks like. You define a particular feature through your filter, and this makes CNNs rather special in the whole field, and is one of the major reasons why CNNs are so successful in the field of deep learning. So now we can move to the code. Okay. So yeah. First, we have some basic imports. So this is the code that I've written. You can find it in your 04CNN directory or folder. And this is the full module. We'll go into, so it has the imports, obviously, the CNN class, and then the network class, and finally we test or train the module. Okay, so what I've tried to do is I've tried to keep it as close to the code from yesterday's session for the feed-forward network. Uh, so the point here is that when you're using PyTorch or like any similar library even, they have a lot of things predefined for you. So you can see that I'm importing to Torch here. Then I'm also importing these operations like convolution 2D defined in con 2D. Then you have ReLU, the activation function, then the max pool operation, uh, then the linear layers, and we'll be using a particular loss called MSE loss. I've explained what it means here. So it's the mean square error given simply by the mean of the difference square, difference between two different, let's say if this is X and Y are two different matrices, so or two different values rather, let's just call it that way. Then you take a difference, you square them, take the mean, that's your mean square error. Yesterday, I think we used BCE, that was binary cross entropy. Uh, but today I thought it would be easier to just use a very simple error like this. Obviously, you can experiment. That's one of the major points here. So you can experiment with different layers, different loss functions. And again, we're using this Adam optimizer, but you can use, for example, SGD, stochastic gradient descent, like it was done on the very first day of these sessions. Okay, another thing is CNN data utils. You don't need to worry about this. It's just um, utility that I've written. It's there in data.py, and you can, of course, go through it. This is, again, similar to what Spandan used for the feed-forward network. There's some minor modifications. You can go through it, but you don't need to worry about that right now. And we'll perhaps be plotting some things in the middle. So for that, matplotlib. Okay. Now we have this CNN class, and you'll note that there are some values here which are set to none, like we have been doing for the past 2 days. So you can try filling them in on your own as we go through this based on the knowledge uh, in the previous section of this talk. Uh, and Anyway, we'll be seeing what these particular parameters would take, what values these parameters would take as we go through this. So first, let's define the CNN class, the convolutional neural network class. So as we did yesterday, we'll define a class which will inherit from module. Module is simply from torch.nn, the base class for all of these PyTorch neural network models or architectures. And in there you have the same init. This is a constructor, and you initialize the superclass, which is module, to this line here. You don't really need to worry about that, uh, all that. The main things are from, okay, let me toggle line numbers here. Okay, so the main thing here are these components starting from line 4 to line 9, and then obviously the forward pass function. So what we'll do is we'll define a network. What we'll do is we'll define a network with two convolution layers. As you can see, I've defined a con1 with which is a con2D layer, then con2, and then we'll also have two final dense layers or linear layers. The activation function that we're using is ReLU, as described previously, and then we obviously have a max pool operation. So if we go back to this image, you see that all of these convolution steps have convolution, ReLU, and then pooling. So for the sake of simplicity, what I've done is I've only defined one pooling operation here. We'll be using the same pooling for both of these convolution layers, as you can see in the forward function that we define here. So this function here defines a forward pass through the network. So for an input, let's just call it x. What you do is, okay, another thing is you'll notice it may seem a bit weird to you why we're using the same variable again and again, but it's just for the sake of convenience. You can obviously name them differently. But for the sake of convenience, let's stick with x throughout. So what we do, what this network would do is for an input x, you first pass it through a convolution layer with these parameters, and we'll come to what the parameters mean in a second. Um, so this is the first layer with the convolution operation, the activation function, which is ReLU here, then the pooling operation. Then you have another layer with the similar sets of actions, and then you pass it through a dense layer. But before that, we have something that we need to do to this input, which I'll explain in a while. And then obviously you have the linear layers with again the ReLU activation, then the final output layer. Since it's the output layer, we won't have any activation there, and then it'll return this final output, which will simply be the probabilities, the class probabilities for the cat and no cat class. That's the task that we've been trying to solve here. Okay, so coming back to the definition of these different layers, you see that con2D, we have con2D, max pool 2D, all of these take several parameters. So what do these mean? So so the very first one, we have in channels 1, out channels 32, and then kernel size 5. Okay, let me go to the documentation of these. Okay, if you're in a Jupyter environment, if you want to see what a particular if you're not sure about what a particular variable or a class or a function does, what you can do is simply type a question mark and then the name of the particular class or a function, and then shift enter. So okay, I haven't imported this, I suppose. Let me do that and then run this. So you can see it'll show you the entire documentation. So you have multiple things here. And I have used in particular just three things. Let me collapse this: in channels, out channels, and kernel size. Okay, so the main documentation is here. Okay, so the parameters, right? So okay, okay, this doesn't render the full mathematical or the later expression, but I suppose it's fine. So first of all, you have in channels. So since I've said that we'll be dealing with grayscale images, so we'll only have one image at a time or one 2D grid at a time. So that's why I've set in channels to 1. For RGB, you can set it to 3, or I mean, it's up to you if you want to tweak it. And then out channels 32. So let's just go back to the documentation here. Okay, let me just search out here in the documentation. All right, so we have args. Yeah, okay, long documentation, but you can find it here. So this is the number of channels in the input image. For us, it will be 1 because grayscale. Then you have the out channels, which is the number of channels produced by the convolution. So as I said earlier, that if you have, okay, let me uh, is slanted. Right, so for a particular image, the final feature map that a convolution would produce, it need not be, even if this is 2D, we have a 2D filter, the final feature map that is produced, that need not be 2D. So it can be, let's say in our case, it can be 3 dimensions. It can be as many dimensions as we set the out channels to be. So in this case, what we'll get is coming back to our parameters here. So we have in channels 1, out channels 32. In this case, the let's call it H and W. Let's stick with this, and then whatever this may be. Then in the and after pooling, so H and W will also change, but main thing is that we have set out channels to 32. So let's say if this is one layer, one 2D layer, and then you have stacks of this. So this length here, let's just call it depth, will be equal to out channels, and so on and so forth for the next layers. Again with con 2D, what we have done is okay. So in the very first layer, we have 32 output channels, and we want to pass it to another convolution through another convolution process. So what we'll do is what this map has to be passed through is, so you have this feature map from the first layer, and you want to pass it through another convolution operation. So for this is depth, let's say, equal to 32. So you have to match it with your filter. So here again, you have to have something like this, a smaller filter. Let me undo all of that. Okay, so okay, this is really deformed, but we'll go with it for now. So let's just so let's say if this is your convolution kernel or filter, then this obviously has to match 32. These are all matrix operations. So you have to make sure, like when we multiply matrices, which are, let's say, mn and something else, let's say k and l here, then we have to make sure that these two match, right? Similarly here as well, when we are doing these operations, even though this is not a matrix multiplication, again this is an element wise multiplication, we need to make sure that some of these dimensions match, otherwise the operation is undefined. So in the first layer we outputted 32 channels, so for the second layer the input channels must be equal to 32, And then output channels is something we can tweak. I've set it to 64 here. And then, okay, we'll move to the next layers. Now let's see what kernel size means. So if you again go to the documentation, kernel size is just the size of the convolving kernel or the filter. So it's just the size of this filter here. So I showed examples with 2 by 2 filters and 3 by 3 as well, I think. You can have it set to whatever size. So here we have set this thing to 5v5 because yeah, the kernel size is set to 5. So this filter size would be 5v5 in our case. Now, so this is the first convolution layer with max pooled. So now again, with max pool also you see this kernel size which is set to 2. So the pooling will, so if this feature map is produced as, I'm sorry, uh, this feature map is produced as a 5 cross 5 matrix with again the depth I suppose was 32. Then if you want to apply max pool to it, you also have to set what the kernel size of this pooling operation would be. So we want a 2 by 2 kernel when you're pooling. So in this feature map, this 5 by 5 feature map, let's just put in some values and anything actually, and then so on. So what we want is we want to slide again in this feature map, rather we want to pool 2 by 2 patches of this feature map at a time. So now when we are pooling, we'll have another window. Let's say this is not a convolution kernel, this is just the pooling operation, and we take two at a time, sorry, 2 by 2 patches at a time, and then we just take the max pool out of it, the maximum value out of it, and then we store it in another matrix. That will be the final output of this layer. And so what we're doing here is we have the kernel size set to 2. That's just the shape of this window that we slide over this intermediate feature map, and we'll have some output from that. And okay, another argument that I'm using here is a stride, the stride of 2. So what does stride mean? So you may be thinking that there are multiple ways in which you can slide filter, even a convolution filter or a pooling matrix, anything over a particular image. So what you can do is you can, let's say if you have different rows, let's say rows and columns. So let's talk in terms of columns. This is like C0, C0, then you have C1, C2, and C3, and so on. Let's say C5. Let's go to C5. And uh, you have a max pool window of like size 2 by 2. So this is your filter, this is your window here that will be pooling from. So this will cover two different columns. Now, if you want to slide across this, what you can do is simplest option is to just slide by one column. So this will be the first step. Then in the second step, you come here. Then in the third step, you'll be here, and then you pool across all of that. Another thing that you can do is, let me undo this. Another thing that you can do is slide across two columns. So instead of, and so you won't have any overlap in this case. So you'll have something like this. Then in the next one, uh, again, so there are multiple ways to handle. So since this is 5 and your kernel is 2 by 2, and what you're doing is you're jumping across this column here. So basically the stride is set to 2. So this is where your stride is set to 2. So if it was 1, then you would be going from C0, C1, then C1, C2, then C2, C3, and so on. Sorry, I'm calling this C5, it should be C4. Right? And then obviously C3, C4 if it were set to 1. But with 2, you're considering two columns at a time. So it's C0, C1, C2, C3. But then you don't have any space. You don't have a C5. You can't move here. So there's another parameters that helps define how you're doing this. Let's just go to the documentation for Maxful 2D. And here you'll see, okay, stride. So, okay, again, the rendering is not good here for some reason. So this is a direct. Okay, so this is the formula that can be used to uh, define or determine the final output size after this pooling is done. So okay, let me do one thing. The official website obviously should have the formula well rendered. So let me just go there and show you what it looks like. Okay, so I suppose you can see this now. So I'm at PyCharge's documentation for the latest release that they had, 1.7.1. And here, it's the same documentation, but with nice LaTeX formula and all. So the output is defined again simply by this particular formula. It looks a bit complex, but you can try putting in some values here, some arbitrary values, and then calculating it for simpler cases, and it'll come out. It's not that difficult to compute this. And okay, let's go back to the yeah. So with stride 2, there are two ways to handle this. Okay, so with the documentation render, I suppose it should show up. Yeah. So there's uh, sorry, another parameter here called padding, which handles how the edges of the matrix, how you pool near the edges of the input matrix. So I think the default here is padding is 0, as you can see here. So padding is set to 0 by default. So in that case, what will happen is it will lose the information at those edges. So if I go back to the Jupyter notebook here, yeah, and collapse this. I've set this right to 2. So what this will do is not consider this column at all. So if this is a 5v5, uh, if it's a 5 by 5 matrix here, then C4 and let's say this will be R4. These two will not be considered at all. They'll have a window moving like that, then your window will come down here, and then you'll have this, and then you'll have 4 values out of this. So this will comprise your final output with 4 different values here. Um, and so this will be a 2 by 2 output if the padding is set to 0. Now, if you did pad it with some value, let's say, uh, okay, in this case, you can, let's say, if you pad it with something like, you can define the way you want to pad it. Let's say, if you want more granular control over this, let's say if you only pad on this side, add a column here, let's call it a C5. Then with a stride of 2 again, you can still cover these two columns. So you won't lose out. So you'll only have zeros in the final column that you added, but you won't lose out on the information contained in C4. And the same goes for R4 here as well. But again, these are all parameters that can be tuned by the creator of the particular class. So here I don't need to take this as 2 or I mean, I can change it to whatever I like depending on the problem, depending on the kind of information I'm looking at. So I can set padding here as well. It's again up to you. These parameters that you're seeing here, these in channels, the number of channels, the kernel size, the stride, and later on the features, the number of features. These are all called hyperparameters because uh, these are what you tune in order to uh, get better output from your neural network. So so for the example today, I've used this because at least in my experiments, I got best results with these kind of parameters, these values. So okay, so that's what kernel size and stride do. And okay, another thing is even in conv2d, you'll find that it has all those parameters. Here as well, you'll have stride and padding. So they mean the exact same thing over there as they do with a pooling operation like max pool. Okay, so now let's move on to the linear layers. I think Spandan explained it in yesterday's session. So here, one thing to note here is that we do not know what the number of in features is, and the reason for that is simple. We currently our data is going to be set of 50 cross 50 grayscale images. But after all of these operations, we do not know what the output will be as we reach the first fully connected layer, or first linear layer. So for the time being, I've set it to none. You can think about how you can uh, get that value, but we'll be doing that in a short while. And okay, so and then the out feature. So this is again something that we can choose. So I've set it to 512. It's a nice part of 2, as I've been doing across here. And then again, the linear, we need to match these two. So it's 512 again. Then the out features is 2, because again, we have only 2 classes, cats and no cats. And then for all of these, I'm using the same activation function, that is relu. All right. So we'll, okay. Now we can do a bit of calculation here. Or rather, let's just first, in features we are not sure about. So let's just put something randomly. Let's just call it, how's- this is just a guess. It doesn't have to be close to what the actual value is. We just need the whole thing to run once. So what we'll do is we'll set this to 1,000, and before this step, let's just print the shape of x. All right. So, okay. Let's okay, we'll get to that. Let's first consider what the network class looks like. It's practically the same as what it was with the feed forward network yesterday. There are not a lot of changes. I think I mentioned earlier that the loss function is now the mean squared error loss, so MSE loss, instead of BCE with logits that was used yesterday. So I think I mentioned this. I've defined it, the loss function somewhere here. Loss function is none. So okay. Is it a parameter? No. All right. So okay, I can just make this MSC loss. Then okay. So what am I doing here again? So the model is, we are using the CNN module that we just created. Then the epochs, the amount of times you want to run through the entire data set and optimize the model. That's the number of epochs. The learning rate again is how quickly we want to try to find the optimal parameters for our model. That will be defined, that will be adjusted by the learning rate here. So I'm using default values like 0.01, and epochs, number of epochs I've set to 5. Then optimizer, as with yesterday, it's Adam with the same sort of syntax. Only thing that is different here is the loss function, MSC loss. Now, yeah, okay. Again, you do not need to worry about what this CNN data utils is doing. It's just here to load data. So you'll have 2 sets of data. You'll have the training data as well as the validation or testing data. So what this will do here is it'll load the train data, which will have 50 by 50 images, uh, and with labels, and then you have the test images and the labels corresponding to those images. Okay, then we have the train function here, and as with yesterday, we have very similar syntax. So we'll be running 2 for loops over the entire data set, and for each of the image, we'll be calculating the model output here. We have initialized these already, so let's just move to this. We'll be calculating the model output. Then, okay, so these lines I suppose I explained, but again, you do not really need to worry about this. So what this does, this op.0grad does is it sets all your gradients. So what Adam is simply, you can think of it as simply a modification of gradient descent in a way. So what op.0grad does is it sets those gradients to 0 before you initialize training on a new example, so that the training process is stable. And again, this is not something you really need to worry about. Then loss function, which is set to MSC loss, we are calculating loss over the output and the target, output from our model and the target. This is what we'll be optimizing. And okay, the optimization occurs in, or rather is invoked in this step, op.step. But before that, there's this loss start backward. So, uh, okay. So I think, okay. this is again something that is part of how PyTorch handles things. But just as a brief explanation, what this is doing here is taking those gradients and then propagating it back to the earlier layers. So okay, now I can kind of draw what the network looks like. So you have an input image. This goes through our CNN. Our CNN has first convolution layer. This will be, let's call it C1, and C2, that's another layer. And then this is connected to a set of dense layers. And then you have finally just two neurons. So this is densely connected here. Sorry, these two. And then you have just, let's say, a particular window. You'll have feature maps. And here as well, this need not be 2D, as I mentioned earlier. So you'll have feature maps here as well, stored in this layer. Then all of this is connected to this. So this is basically what our model here looks like, would look like if you represent it graphically. And okay, so this is the output. Let's just call it F2 or output layer. So yeah, what lost backward is doing is first you're collecting everything. Sorry, calculating everything in the forward pass. This will be your forward pass. And before you optimize the parameters, what how PyTorch handles things is you propagate all the different errors that you got in a backward pass throughout all of these neurons. So that's what this step or this function does. It simply collects all these errors and then propagates it backwards, accumulating it. So yeah, in the forward pass it accumulates the errors, in the backward pass it propagates it's backwards across the layers, and then the overall parameters are tuned in the op dot step. That is line number 25 here. Then okay, we are printing the epochs with the loss in that particular epoch. Then okay, now we have the test method here, where we'll test it on the validation data or the test data set. So we have model, that's self.model, then the test data and test labels. And again, we have something like torch.nograd here. So now since we have a trained model and we just want to run it on uh, some data, some input data, we do not really need to tune the parameters. We do not need to affect the parameters in any way. We just want an output. So uh, before doing that, what we can invoke is this function torch.nograd. What it does is it tells PyTorch that right now we do not need to alter any of the parameters, and the model is ready for being run on any random input. So this is just like a context manager. It's in Python, we call it a context manager with the syntax. You can just as well have it in separate lines. You can first have torch.nograd and then have all of this. You do not really need to use a context manager, but there are reasons of efficiency and also writing good code why you should prefer a context manager. So after this, we have again a simple loop to loop over all the uh, examples or all the inputs in the test data set, and then simply uh, gather the predicted classes and count the number of the classes which were correct, and then simply calculate accuracy by taking a ratio of the correct total number of correct outputs by the total number of inputs that were given to the model. Okay, and we're rounding it off, but that's unnecessary. Then we have okay, so here this is the setup that we have here. Now let me see if there's anything that requires modification. No, it looks fine. Okay, so then we'll be training the model. So you can see that here I've set the default values of epochs and learning rate to be 5 and 0.01. And again, that these are like defaults that people usually start with 5 or 10 epochs and learning rate around 10 to the power minus 2 to minus 3, but it depends on your particular case. So here I've actually modified it to 10 epochs and 10 to the power minus 5. And this is how I'll be initializing our network with this line 1 in this block here. And then we print a summary of the model like we did with FFN yesterday. Then we train and then we test it. So, okay. So, okay, now we come back to this CNN module. So as I said, we do not know the exact number of features that we need to put into this linear layer here. So I've just initialized it to be 1000. We'll be modifying it. But before that, we also need to do something here. So coming back to the how a model looks here. So after we pass it through our convolutional layers, and then when we want to pass it to the fully connected layer over here or the linear layer here, we see that the output here of the final feature map that our convolutional layers gave us, uh, it would be in terms of obviously in terms of the overall input shape and all of that and the parameters that we chose here in these three lines. But also before we pass it here, we need to linearize this entire feature map. And by linearize, I'm referring to the same Latin operation that I mentioned somewhere before. So uh, what we'll be doing here in this line 24, is we'll be invoking, uh, I mean, we'll be flattening this x, but there are multiple ways to do it. I'll be doing it in a specific way. You can also use several built-in functions that PyTorch or Torch has. Uh, but before that, let's first see what shape exactly do we need x to be. So, okay, let me run all of these. Before that, I'll restart the kernel just to be sure there's nothing amiss. All right, so we do not need this. So let me just get rid of this. We have imported, no errors there. Okay, let me do one other thing. Let's just exit after we print the shape so that we do not have to go through the entire training process. All right, so I suppose, okay, this is interpreted, this is done. I'm running this block over here. Okay, let's see. I think we have a slight issue here. We'll be back in 2. Okay. There's still some issue here. Okay. Oh, sorry. Okay. So is it part of this? Nope. Okay. I think there's some issue with the video. So we'll be back in around 5. We have to fix this. All right. So, okay, so the stream should be back up. Okay. So So we were at this step. I'll just run the model and ignore the error for now, because obviously we have the error says, if you go down and you see, it just says non-time object has not attributed dim. The reason for that is this line in particular, as it points out, x equals none, and then it causes errors over there. So our goal was to see what the shape is after passing it through the two convolution layers, and the size has been and the shape has been outputted here. So that's 50 by 60. So 50 is from the batch here, the batch size that we chose. So we are putting in 50 images at a time, passing in 50 images at a time to the network. So through our data utility class. So that's where the 50 comes from. And then we have 64 channels, as I set here. Out channels for 64. That's where that 64 comes from. And then we have the 9 by 9. So this is the actual shape of the uh, 2D stack. So each of the, so it's a 64 by 9 by 9. So let me just get here. So the output here at this stage is 64 for a particular input by 9 by 9. So it's a three-dimensional matrix. You can take it like that. 64 is simply the number of output channels. But if we just consider the 2D stack, then the shape of each 2D matrix is 9 by 9. So now we have the shape, and now we know the value. Now we have to calculate the value that we can put instead of this in features, this dummy value that we put in here. It's clearly not 1000. 64 into 9 again multiplied by 9 is clearly not equals to 1000. So we'll now go back to the Jupyter lab here. All right, so now we simply just calculate what this value is. So let me create another cell here and see what, so multiplied by 9 divided by 9 is, that's 5184. So what we can do is copy this, not cell, copy this value, control C, paste it here. So this is done. Now this also needs to change. So I mentioned that we need to flatten the final output from the convolution layers before we pass it into the fully convolution layers. So for that, what we need to do is, again, there are multiple ways to do this, but what I'll be doing here is a rather simple trick that people use a lot. So there's a function in Torch and even in NumPy called view. What it does is it creates a so it's kind of like the slicing that you do. For example, if we have, let me just give you a short example with NumPy. So I create a matrix, let's call it A, np dot uh, once of shape 4 by 4. Then let's see what it looks like. It looks like this. Let's use this cell here. So uh, to np dot view, and let's see what the syntax of this function looks like. So I think yeah, the doc string for this, the documentation for this is here. So you can see what it creates is it creates a new view of array with the same data. So it's kind of like slicing. So you may know that in NumPy and even in Torch, you can use indices to refer to a particular element. If I do A22, so it will refer to this is the 0th row, 0th column. So this is the second column, second row, and then this is the second column. So this A22 is going to refer to this element, and then we can do similar stuff. So if I write a colon instead of a particular integer there, then what it'll do is it'll consider the second row. So this 2 refers to, so you'll have the third row or the row number in terms of the zero indexing, it will be row 2. So you'll have this row, and all this colon basically means all. So you have all elements of this row. So that's what it produced. So view is kind of like that. It will create same thing, but so we can do it like this as well. So sorry, not that. Let me just okay this sec. the documentation. So we don't want to change the D type. We want the particular value. So let's say 2 comma, sorry, my bad. Okay, sorry, this is in NumPy, right? So this should create with the same data. Okay, so here it's a bit different. This can be used to transfer between data types. So in Torch, you can use it for these slicing operations as well. So let's say if I do Torch dot random, I suppose should exist. We do not need this. Let me remove this. Okay, apparently I did not import Torch. Random dot random, I suppose. Sorry. Okay, let me see. Let's just see if it exists first. All right, so it does, and then the size. Okay, it's a sequence. All right. So this is what A looks like. Now let's create a view into this. So it will simply be A dot view, and let's just do this. So you can see what it did. It -1 simply means the last dimension. So for example, if it were a list, simple list, let's call it 1 2 3 4. Let's call it LST, not A. And we did LST -1. It will refer to the last element in that list, so 4. So what here, it's not the element that it's referring to, it's referring to a dimension. So this -1 here means that the last dimension, so the shape of A, it's just out that A dot shape, it's 4 and 4. So what you want to do is take the last dimension and then concatenate in a sense. So you have a stack of these rows, you just stack it together like columns, or column wise. So you have these 4 elements first. When you run a view -1, you have these 4 elements first, then you have these 4 elements, and then so on. So that's what this does. Now we are also specifying the full size that we calculated out of after printing the shape here after line 20. So we'll use that directly, and then we'll get a flattened output. So I can also do one other thing here, that is print x dot shape, and then try exiting modular. Okay, I suppose this restarted. What happened over there? Let me. Okay, that's done. Now if you're training, I'll probably have to stop it, but we'll see. Okay. Okay, it's busy, so I suppose it's. Let me remove the print statement then. Not. And this. We'll take a look at what the output is with another example, I suppose. And now let's just run the network. Okay, so this is the summary of the model, how it looks like. So you see you have a conv2D layer with the pooling operation. This is just the different components in the model. The two layers of two convolution operations, then the pooling, then the fully connected layers, and we're using this as the activation function. Then the details on the training for 10 epochs that we chose here with this learning rate. So we see that the losses going down, but here you see that it again rose up. So let's see. Let's come back to this image. Here, but so what we want to do is to simply reduce the loss. But in this case, we see that the loss did reduce to a particular point, but then it rose back up and then it kind of fluctuated. Although in the end, we did end up with the least loss overall. Uh, but if you want to avoid that, then we have several solutions for that. So softmax is one thing that helps with that. If you put this layer, this is not really relevant to the CNN part, so that's why I ignored it in this session. There are other solutions like uh, adding something called dropout layers. So you can also add so yeah, let's get back to the output. So what you can do is you can have dropout layers. So you'll have a particular threshold. When the loss function crosses that threshold, you simply stop the training. So you can set it to, let's say, something like 0.2, 0.22 here or something. Then it'll, even if you specify 10 epochs, it'll just drop out, or the network will stop training right after it hits a particular loss ceiling. In any case, this was just a simple example, so we don't need to consider or concern ourselves with all of that. Okay, so training was done, then it also tested it on the dataset, on the test dataset that we had, and we find that the accuracy is 65.41. So, okay, let's see what the data actually looks like. So, do I have? Okay, let's just import NumPy. So the data is stored in data.npy here. So it's a NumPy format. So what we'll do is uh, load it into a variable called data.npy. And let's just print out, let's say, the shape. So, okay. So what this means is we have 3,995 images in this, and we have two classes. So overall number of classes is two. So this is the image plus the class that it belongs to. So if I just print out the first element in data, you see you have an array here. This is the image, the grid representation of the image in terms of the pixel values, and then you have another array here with 1 0. So if this one is in the first column, that simply means it's a cat image. So what we can do is we imported matplotlib earlier. So let me just plot this, plot.im show data 0 uh, 0. It's a 50. You can see the scales here. They go to like 50 here, then 50 here. So it's a 50 by 50 image of a cat, and it's grayscale because you can see that if I simply do data 00 dot shape, print that out, it's just 50-50. You don't have an extra 3 here. That simply means it's grayscale. And then yeah, we can also print out the label. So we saw that the label was 1 comma 0. So that simply means it's a cat. If it was 0 comma 1, then it should be a not cat or some other image. uh, okay, so that's how the data looks like, and you can see that this is a pre-processed data set, but in most cases you have to pre-process your data yourselves. But for this example, again, we do not really need to worry about all this. Now the training process does not take too long, and even with the total number, even if with these many parameters that we have, so you can simply take a product of the parameters that we have set here. So you'll see that what we are finally outputting from our convolution layer is these many outputs. So it's not a lot, but still, even for these many parameters, the training step does not take too long. And the reason for that is if you look at some steps here, I suppose, yeah, okay, for example, here, this function to CUDA. So it's a bit more advanced to talk about this here, but it helps. If I just get rid of this part, you'll see that the training, okay, I'll reduce the number of epochs as well. Let's say, let's do it for 1 epoch and compare. We just need to train it, not test. We can also avoid printing. Okay. Let's do it like this. Let's define our net over there and change it over here. Oh, sorry, not that. I'm gonna go up. So, okay, this was there. And to recompile this block, the network block, stop this. Is not needed. Just we have defined a net over there. Okay, so this is, oh, okay. This is not set to CUDA. Okay, so CUDA here basically refers to that the particular matrix that we are dealing with is on the GPU. You may have heard that GPUs are being used extensively for machine learning and deep learning. The reason for that is they are massively parallel. So they have CPU may have 8, 16 cores or even 32 or 64 cores at best, or even more, but the price to value ratio goes down by a lot. But with a GPU, you get thousands of cores with, and in most cases, they're cheaper than um, comparable CPUs. So that allows us to massively parallelize this whole operation. That's why if you train, so what this step here is doing is simply moving our model to the CUDA. So to the GPU, to CUDA, this is actually for NVIDIA GPUs. So this is in particular for a company called NVIDIA manufactured GPUs. And I'm using this here because for even for the these many final even for this particular length for the feature map, if you train it on a CPU and if you want good enough results, uh, you'll have to either decrease the epochs or increase the learning rate, or tune some other steps, tune some other parameters here. We don't want to do that, so we can simply run everything on the GPU. So, and it speeds up the process by many orders, in fact. So, okay, let's do this again. And perhaps not time it here, or maybe we can. Yeah, okay, so overall time was half a second, less than half a second for a single epoch. Even for 10 epochs, if I just go back to what I had here, even for 10 epochs, it won't be too long. Yep, you can see that even for 10 epochs, it's less than 5 seconds. So it's like half a second per epoch, which is pretty impressive. And with CPU, it will be much, much higher. Okay, so we do not need this. We saw how the data looks. We have trained our network as well. Okay, let me remove commands here. Hit again once and then see the final accuracy value that we get. And it's about 65%. So this may not look impressive, but I mean, the reason why this is low is because first of all, the data is just 50 by 50 images. So it doesn't have a lot of information per se. It's a very diluted version of the actual data set. So I think I mentioned the data set that we're using. Okay, not here, I suppose. Maybe in data.py. Yeah, so this is the Kaggle dogs vcats dataset. You can go to this link. They have full description of the dataset. It actually has approximately 25,000 images. And what we're using, as I mentioned, was somewhere around 3,995 images. A very small subset. If you increase the overall data size, I mean data set size, then obviously you can expect improvement in the accuracy value. Uh, Another thing is we can tune these parameters. So I would encourage you to tweak these values over here, the number of channels, the kernel sizes. Basically, for all of these uh, layers, you can, if you're unfamiliar with this, just run question mark the name of the layer. You'll see the documentation, or go to the website. The PyTorch documentation is really good. And then you can try figuring out what the exact parameter value should be, and then try running it for different sets of parameters. that constitutes our hyperparameter tuning. So it's another step in this whole deep learning pipeline. And yeah, you can see if you can get better accuracies on the same data set. And as you advance through it, you can also try to modify the data in some way so that you get much better results. Okay, so suppose that is all I wanted to cover here. Yeah, so there's a link here. In fact, let me just open it. This is on the convolution layers, how the filters actually work on different uh, layers. So there are multiple things here. This convolution, transpose, convolution. For this session, you do not need to worry about what this is and what dilated convolutions are. All you need to focus on are these. So what the paddings and the strides do basically. Kernel size, that's very simple. It's the size of the filter. Uh, and the channels, input and output channels we discussed. So you can try to understand these. It's really simple. And I think, yeah, that is all I wanted to discuss today. So just as a summary, we went through how computers see or how computers would analyze an image that we give it to analyze, and what these convolution layers do, what is the role of the ReLU activation here, then what a pooling operation looks like, and then finally what the classification steps look like. So the flatten layers, that would be the linear layer, which are fully connected, and then the number of neurons in the final output, which correspond to the number of classes that we have. Um, Other than that, if you have any questions, you can obviously direct it towards me or the volunteers. Um Otherwise, we can stop in about 5 minutes.